Hello everyone, my name is Melina and I will present here part of my PhD project entitled Seeing the Forest for the Trees, disentangle the contribution of species, space and time to their variability in tree vital rates. This project is advised by Lisa Huisman, Paulo Prado and Sean McMahon with the collaboration of Mark Weisser, Stuart Davis and Alexandra Delat. It is partially funded by the University of Regensburg, University of São Paulo, the Smithsonian Institute and the Forest Geo Network. The fundament of this project is related to the importance of understanding global forest dynamics and the consequences of these dynamics to the global carbon cycle. As a considerable amount of carbon is stored in tree biomass, the magnitude of both carbon sink and stock of forest depends on tree demography, that is, how trees grow, die, and reproduce. Here we represent tree demography by three vital rates: growth, mortality, and recruitment. Forest ecologists already know a lot about what may affect forest dynamics, introducing variability in tree vital rates. If we collect a list of processes and mechanisms that can produce variability in any of these three vital rates, we will end up with groups of related sources. For example, one of the most obvious sources of variation in vital rates is the difference among species. Trees from different species may have different vital rates because of life history strategies that may be related to functional traits. So, one species may grow fast, another slow, and it will add to the variability of the forest vital rate. We can also have spatial variability in vital rates. For example, when we have habitat variation or areas with more nutrients in the soil that will allow a faster growth for trees in there. Additionally, we can have temporal variability in the vital rates, that is, trees in different time periods will differ because, for example, a drought period, some disease that spread in the fourth and center year, and so on. In addition, we can have the interaction between this grouping source of variability. So we may have trees of the same species different in vital rate depending on the area, which may be caused by environmental filtering when one species performs better in one certain habitats than others. We may have trees of the same species different in vital rates depending on the time period, which may be caused by an asynchrony in species response to a drought event, for example. And also, we may see variability in vital rates in a forest not related to the species, but the interaction between the spatial and temporal component here. Trees in the same area may vary depending on the time period, for example, in gap dynamics, when recruits increase in general in the surrounding of fallen big tree. Finally, we cannot forget the possible individual variation in the vital rate, which can be caused, for example, by ontogeny, when the vital rate depends on the age of the tree. But also because we are dealing with real data, in this group there may also be measurement error at the level of the individual, which is not unusual in large inventory forest data. All the sources of variability may be more or less important depending on the forest, the vital rate, and many other specific contexts. But their complexity makes it hard to see the forest for the trees. Many of the studies so far claim for some mechanisms to be important in understanding forest dynamics, which can be mapped to one of or more of these grouping sources here. But we still don't know how these components are important in relation to each other. For example, how in general the difference among species is larger or smaller than the spatial variation in vital rates, and which of these groups contribute more to the variation in the vital rate. These comparisons can raise new insights about the relative contribution of or importance of the mechanisms itself. With that in mind, we started the study with two main questions. What is the relative importance of the source of variability in vital rates? For that question, we aim to quantify or decompose the relative importance of the different sources of variability for many forests around the world. And second, we want to understand if the quantified relative importance of each group vary depending on the spatial scale of the study. To answer that question, we compare the grouping source of variability among vital rates and spatial scales. Spatial scale here is important because it's known that many processes driving forest dynamics are scale dependent. To achieve that goal, we analyzed so far data from 13 forest geodynamic plots around the world, and we are currently expanding the number of forest plots. The advantage of this forest dataset is that they follow a standardized census protocol where all trees above 1 centimeter in diameter at breast height are measured. These forests are representative of very distinct types, ranging from tropical to temperate and with very distinct climates. but especially they vary in 3 orders of magnitude and species richness, from less than 20 to more than 1,000 species. Here we have an example of a map of a forest park in 2 periods. Here is the time interval between the censuses, the location of each tree, for instance here for 3 species. The spatial component is the quadrant size, as we can partition the entire plot in quadrats of different sizes. Quadrant size will be our spatial scale, and we use 5 scales of quadrant size, from 5 to 5 meters up to 100 by 100 meters. Briefly speaking, for each forest plot, we calculate the annual growth, mortality, and recruitment using mixed effect models. In this model, we use the grouping source of variability, that is the components, as random effect intercepts. With the results of this model, we calculate the variance partitioning component, that are the proportion of the variance in the vital rates for each model component. As we can see here in this example, we have all the grouping source of variability represented now as VPC that sums 1. For more details about the methods and modeling procedure, please don't hesitate to send me a message or email. Here we have the results for all forest plots for the quadrant scale of 5 by 5 meters as an example. Because many forests don't have a long time series of censuses, we don't have the temporal component in these models. In the x-axis, we have each forest plot in a certain period interval. Each row is one vital rate, and these columns are the components, so the grouping source of variation. In this panel, we can see that for all vital rates, most of the variance remains in the residual component, followed by variation among species. For growth, the VPC of the species-space interaction is relatively larger than for the spatial component alone. However, for mortality, the spatial component seems as large as the species-space interaction component, and for recruitment, this relationship is inverted, while the spatial component is higher than the species interaction. What happens if we increase complexity and also account for time? For a more complex model, we have so far 4 forest plots with more than 4 consecutive censuses. The panel is similar as before, with the addition of the time component in the columns. We see here that species component is still larger than the other components, but the species-space interaction component is more important for growth only. But now the VPC of the species-time interaction becomes larger for recruitment and mortality. Now let's see the comparison for different spatial scales. In this panel, we see the box plots of the results for all forests with the increase of spatial scale in the x-axis. We can see that the VPC for components with space decrease with the increase of the spatial scale and the residual increase. It's interesting to see here that for mortality and more pronounced for recruitment, the VPC for the species-space interaction is higher for the intermediate 10 by 10 and 20 by 20 meter scale, spatial scale. Also, as expected, species VPC doesn't change with spatial scale. With this simple analysis, we could see that the source of variability and vital rates among forests are similar despite large differences in climate, environment, and community size of these forests. And what we have here is the plot with the mean VPC for each component, for each spatial scale, and vital rate. So, the main source of variation in vital rates, excluding the residual, is the variability among species. The results are similar among hyperdiverse tropical forests with more than 1,000 species and low diverse temperate forests with less than 20 species. It may suggest that forests have similar demographic niche or life history strategy spectrum, regardless of the number of species in the community. Another interesting result is related to the differences among species in their relation to the spatial variation, represented by the species-space component. It was relatively very important for growth, but only for the small spatial scales. And for mortality, and more pronounced for recruitment, this component was a bit larger in the intermediate spatial scales. We may interpret this here as environmental filter acting at different scales, and its relative importance vary among vital rates. So, if someone wishes to, for example, to study tree growth by the relationship of functional traits and environmental gradient, we would recommend the smaller spatial scale possible, because it's probably at that scale where most of the variation in growth can be explained by trait-environment relationships. The grouping components with time, especially space-time and space-time interaction, seem more important for recruitment and depending on the scale for mortality, but not so important for growth. This suggests that gap dynamics may be an important mechanism for recruitment regardless of the species being recruited, and also that there is more asynchrony in species response to temporal change in recruitment, which may be related to climate filters making trees of the same species recruiting more or less depending on the time period. Although we could decompose the source of variability into spatial, temporal, and species component and their interactions, around 50% of variation in vital rates remain the residual component. And there we cannot separate the variability attributed to the individual variation as ontogeny or measurement error in data collection. However, we believe that ontogeny can play an important role in the residual component here due to the well-known differences in vital rates for young and old trees. With a simple analytical approach and data of forests from all over the world, we could quantify the relative importance of the different sources of variability in vital rates. That can provide a first approximation of the relative importance of many of the mechanisms that affect forest dynamics. We saw that difference among species are the most important source of variability in all vital rates irrespective of spatial scale. We also saw spatial and temporal sources of variability are only important with interactions with other sources, as space-time and species-space component, and their importance vary depending on the vital rates and the spatial scale. For the next steps of this study, we want to look better into possible difference among forests and related to possible drivers as environment, climate, and community metrics. We want to analyze more forests to have a more comprehensive overview of global forest patterns also. I want to thank to the colleagues from the Laboratory for the Theoretical Ecology and Quantitative Ecology for discussing previous versions of this project. We also thank to the principal investigators of the Forest Geoforest plot for the collaboration in providing the valuable forest data. Thank you all for listening. I will be glad to answer any questions or comments you have. Stay safe and have a nice conference.